Welcome to the 11th week of live interactive session on the course Integral Transforms and their applications. So I will be going through some demo problems according to the last week lectures. The topic for the lecture is basically the fractional derivatives and the fractional differential equations. So I will demonstrate how to solve these demo problems, and I hope that will help you understand the concepts much better, and will help you to solve the assignment problems. So without wasting time, we will start now. So the first problem I have here is, if f of x equal to x square, find d raised to minus half f by dx raised to minus half. So where here the operator is, so the d raised to minus half by dx raised to minus half is basically the d raised to minus half with respect to x. So if you have watched the lecture videos where the operator is denoted like this only. So the function is given, it's x square. So options are also given, so I may give you some time for try this out, and then I will show how to exactly solve this. So this is actually a simple problem, so you can try yourself. So I will give some time for this. I hope before coming to the lecture you all have watched the videos for the week, so you might have a better idea of the formula and concepts. So anyway, I give you a hint which formula you could use here. From the basic principles, if you have noticed that taking the derivative of a polynomial function x raised to n with integer order, we obtain a relation like beta factorial by beta minus 1 beta minus alpha factorial times x raised to beta minus alpha, and which is extended to any beta and alpha, any real numbers. So which we can call it like gamma of 1 plus beta divided by gamma of 1 plus beta minus alpha x raised to beta minus alpha. So let us first try this expression. Here we have alpha equal to minus half and beta equal to 2. Basically what we want is d raised to minus half x square. So if we substitute the values here, we will find d raised to minus half x raised to 2 is gamma of 3 divided by gamma of beta minus alpha, so that is 5 by 2 into x raised to beta minus alpha, which is 5 by 2. So gamma of 3 is just 2 factorial, which is 2 divided by gamma of 5 by 2, we can write as 5 by 2 times 3 by 2 times gamma of 3 by 2, where gamma of 3 by 2 we can again write as 1 by 2 times gamma of 1 by 2, and gamma of 1 by 2 we know it is just root pi, then x raised to 5 by 2. So if you reduce this, you will get 8 by 3 times x raised to 5 by 2. And of course you know that is 8 by 3 root pi. Yeah, it is not correct. So this is an issue because this formula is applicable when alpha is greater than 0. Okay, so we have alpha is less than 0, so it is not applicable. Here alpha is minus half, so we shouldn't have used this formula. Okay, so which formula we can use here? So dear, especially we notice here that we have alpha is equal to minus half. So when alpha is negative, an applicable formula which comes from the Riemann-Leibniz integral formula, which is d minus alpha with respect to x, f of x is given as 1 by gamma of alpha integral 0 to x minus t the whole raised to alpha minus 1 f of t dt. So here if you do, it's gamma of minus half, gamma plus half. I made a mistake. Yeah, according to this expression alpha is half. Okay, so it's a gamma of half, then 0 to x minus t the whole raised to alpha minus 1, which is minus half, into f of t is t square dt. So gamma of half, we know it's root pi, so it's integral 0 to x t square by x minus t dt. Okay, so now this we can rearrange the expression like t minus x plus x the whole square dt by x minus t, then integral 0 to x. Again some rearrange 0 to x. So we are expanding the using binomial expansion, x square plus 2x times t minus x. So we will write as minus 2x times x minus t, because we have square root of x minus t in the denominator, that's why. Then plus t minus x the whole square, which is x minus t the whole square. Again denominator we have x minus t square root, then the integral dt. So here again 1 by root pi will keep outside, and we will write it as a group the terms separately. So x square is a constant, and then 0 to x integral x minus t the whole raised to minus half, then minus 2x integral 0 to x minus t the whole raised to half. Dt is there, and here also dt. Then x minus t the whole raised to 3 by 2. Yeah. 0 to x. So first of all, x square, first integral is basically, so x minus t the whole raised to minus of plus 1 divided by minus of plus 1, just half divided by half. Note that because we are integrating with respect to t, we should have a negative sign along with that by change of variables, and the limit we need to apply, that we will apply together for all the terms, which is from 0 to x. So that we will write later, but right now just integrating. Then x minus t the whole raised to 3 by 2 by 3 by 2 with the negative that we already kept in the outside. Then plus x minus t the whole raised to 5 by 2 by 5 by 2 with the negative sign that we already take outside. Then we have to apply the limit where t is going from 0 to x. So now if you notice, if we apply the limit, the higher limit, so upper limit, which is t equal to x, all the terms will become 0, which is inside the curly brackets, and then we have to subtract the limit at the lower limit, which is at t equal to 0. So if you just do the algebra, it will just become x square x raised to half by half, which is basically, I can rewrite as x square times root x 2 minus 4 by 3 x raised to 5 by 2. So this also x raised to 5 by 2. Then the final term is 2 by 5 x raised to 5 by 2. So now if we simplify this, x raised to 5 by 2 we can take common outside, then just 2 minus 4 by 3 plus 2 by 5. So which is 2 into 5 by 5 minus 4 by 3 plus 2 by 5. So 12, 36 minus 20 by 15, so 16 by 15. So it's 16 by 15 root by x raised to 5 over 2. So if you check the option, we have option C as the answer. So every options are identical, the coefficient in front of the x raised to the power is same, 16 by 15 root pi, just that the exponent of x was changing in all the options. It's not the options but the final answer matters. Yeah, so we got the answer. So we should have used this formula in, so you got the reason, right? Because the earlier formula that I have shown didn't work because that is designed for the values of alpha, which is basically that is for alpha, the derivatives which are they are actually for derivatives. So this is not exactly a derivative, this is actually an integral. Okay, because alpha is half, it's a half order integral that we are. So you can see the power is actually raised by half in the x raised to 2. But the formula we have used for polynomials, so that will work only for derivatives. For integrals there is another expression. Let me show that expression. Right now I couldn't find that. I will get back to you with that expression. So okay, so any doubt in this particular question? Okay, so if nothing, we will move to the next question. So similar problem here, but actually we are evaluating the d raised to half of f of x, but the function is now not a polynomial, j0 root x, Bessel function. So the earlier formula that I have shown for polynomials cannot be used here, because that is especially for polynomials, that is the Lacroix formula. But here it is not a polynomial, so I cannot use that directly. Okay, so I might give you a moment for you to try this out. Options are given. Okay. So anyone got the answer? So one hint, maybe you can use the expression of j0, let's say some variable, say s, j0 of s. So you know the series expansion of j0 is basically a Taylor series expansion. So which is this is the Taylor series expansion for j0 of s. So that may help you do this. So let me show how to do this. So first of all, we are applying dx half on j0 root x. Okay, so we can use the Lacroix formula, but let me write it in the polynomial expansion form for j0 of x, j0 of root x, which is r equal to 0, infinity, minus in the whole raised to r by r factorial square, 4 raised to r, then root x the whole raised to 2r, which is basically x raised to r. Now because of the linearity, we can switch between the operators, r equal to 0 to infinity, and r is a variable which is not going to affected by the derivative operator, so we can take that outside, and just that d raised to half is going to affect only x raised to r. Okay, now remember we have seen d raised to alpha of x raised to beta is gamma of 1 plus beta by gamma of 1 plus beta minus alpha x raised to beta minus alpha, right? So here we have d raised to half of x raised to r. Let me call this as expression 1. So it's gamma of 1 plus r divided by gamma of 1 plus r minus half, then x raised to beta minus alpha. So that's r minus half. So since we are taking summation of all the integers. So r is actually basically integer, or r plus 1 is an integer. So gamma of 1 plus r just r factorial. By bottom we need to have gamma of r plus half. Okay, then x raised to r minus half. So gamma of r plus half has a famous formula, because this is a half extension from a real number. So r is actually a real number, or not a real number, integer, and you are adding a half to it. So the gamma function can be simply written. Let me write the expression. So it is 2r factorial root pi by 4 raised to r factorial. So let me verify this expression first. So this is valid for all integers r. So I think I am missing some coefficient. Yeah, it is correct. So 2r factorial square root pi divided by 4 raised to r factorial. So this is gamma of r plus half for any r element of positive integers. So because we are taking summation over the integers, we can use this expression here. So let me call this expression 2. So we substitute this gamma of r plus half expression in equation 2. We will get d half of x raised to r is r factorial x raised to r minus half divided by 2r factorial root by, then 4 raised to r, 1r factor will get cancelled. So this is the expression of d raised to half x raised to r. Now we substitute this. Okay, this was r factorial square. Sorry. Because we already had an r factorial here, and one r factorial will come from here, and they will not cancel. Actually, they will get squared. So now we come back to equation 1, where we substitute in this in equation 1. Let's see. So we are evaluating d raised to half of j0 root x, which is basically summation r equal to 0 to infinity try this, minus 1 the whole raised to r by r factorial square 4 raised to r, then the derivative term, which is r factorial square x raised to r minus half, then 4 raised to r by 2r factorial root by. Now this 4 raised to r will cancel, r factorial square will cancel. The remaining term
right?
So it's 1 by root by x raised to minus half, then the summation of r equal to 0 to infinity minus 1 minus x the whole raised to r by 2r factorial. Yeah. So now it is 1 by pi root of pi x. So the summation, if you see, it's actually 1, then for r equal to 0, then r equal to 1, it is minus x by 2 factorial, then r equal to 2, it is plus x square over 4 factorial, etc. And you can think it as like 1 minus root x the whole square over 2 factorial plus root x the whole raised to 4 by 4 factorial, etc. Which is basically 1 by square root of pi x. And this series you may recognize, this is basically the expansion of the cosine function. So it's cos of square root of x. So the solution is basically cos root x by square root of pi x. So I think the option, yeah, D, which is the solution. So this is one way of doing it. So is this clear? Basically we are using the Lacroix equation here for polynomials, but for that we need to write the function j0 root x in terms of the polynomial expansion. Basically it's Taylor series expansion that we are using here, and just that fact that we need to use this identity because we are evaluating gamma function for integer plus half. So that's the only tricky part that we may need to remember this formula, or we're about to know about this formula. Other than that, everything is straightforward. Okay, so Another way of doing this, let me tell, so that I am not going to demonstrate, but you may can try that. So going to give the same result, should be right. So another way is basically we are evaluating d raised to half of j0 root x. So now you may remember d raised to alpha of f of x using Riemann-Leibniz integral, which is 1 by gamma of alpha integral 0 to x minus t the whole raised to alpha minus 1 f of t dt. Now we are going to use that here. So it's this is d raised to minus alpha. So this is for alpha positive. That means d raised to minus alpha only it will work. So but we have d raised to plus alpha. So what we can do is that we can write it as d raised to 1, d raised to minus half, then the function, which is j0 root x. So first d will be just d by dx. The second d will be 1 by, using this formula we can write it as 1 by gamma of half, then integral 0 to x minus t the whole raised to half minus 1 the function j0 root t, then dt. So since we know gamma of half is a constant and is root pi, we will take it outside. Then d by dx exists, and then 0 to x j0 root t divided by x minus t dt. So this is one way of doing it. But from here, how will you evaluate this? That's a trickier part. Still, see, you can use the expression for j0 root t that we had earlier. Using this expression, there is a, yeah. Use a for expanding j0 root t, and then it will be a polynomial expansion. So you may have to evaluate t raised to r by x minus t dt 0 to x, then which you can write as t minus x plus x the whole raised to r dt by x minus t. So here what we are doing is that we need to evaluate this expression. Now we use the binomial expansion, so which is r p, where p is going from 0 to r minus 1 the whole raised to p, x raised to r minus p, then x minus t the whole raised to r, then we are dividing with x minus t, so dt. So this you may have to write it as like p is equal to 0 to r p minus 1 the whole raised to p, x raised to r minus p, just that 0 to x minus t the whole raised to r minus half dt. So this you can evaluate this integral, then combine with the remaining binomial terms, you will get a solution. Then substitute back that in expression, what is this expression? 3, right? Expression 3, and then finally take the outer derivative, the normal first derivative, and scale it with 1 by root pi, or scale it with the root pi. You will get the same solution as we have got earlier. Okay, so that you may can try. So that's another way of doing it. So I hope that is clear. So we will move to the next problem. So here we have a fractional differential equation. D raised to half y is equal to minus y plus x square plus 8 by 3 root pi x raised to 3 by 2. So find the solutions. So I will give you some time for you to try this out, and then I will explain how to solve this. so anyone have got the answer? Okay, so I will show how to solve this. So this is basically a fractional differential equation. So we can use the Laplace transform to solve this. So take the Laplace transform on both sides. So we'll take Laplace transform of d raised to half y. So let's say this is equation 1. So first we need to take Laplace transform of all the times. Let's represent let Laplace transform of y, which is a function of x, is equal to y cap of s. Okay. So here Laplace transform of d raised to half y is needed, and it's d raised to half we cannot directly take. So we will take split it into d raised to minus half d raised to plus 1 y. If you have watched the lecture videos, there is a problem that have done the same way, that we are following the same method. So because now we have Laplace transform of like a product of operators where d raised to minus half and dy. So we can write it as s raised to minus half outside, then Laplace transform of dy. Okay. Now so this one Laplace transform of dy, we already know this. So 1 by root s we will take outside, then this is just s times y cap of s minus y of 0. Okay, so it's basically if you now take the square root of s inside, it's just the square root of s times y cap of s minus y of 0 by root s. Where y of 0 is not given, we will assume it to be like some number, some constant. We will keep it like that. So this is the Laplace transform of d raised to half y. Now the remaining times, the Laplace transform of y we already told, it's y cap, and Laplace transform of x square. So Laplace transform of x raised to n is n factorial by s raised to n plus 1. Remember that. Okay. So we'll use that here. So here remember that we have done this everything in the time domain, but here the equation is in x. So just like you remember x as a t, that's all. So t raised to n, it's n factorial by s raised to n plus 1. If n is not an integer, then gamma of n plus 1 should replace n factorial, that's all. So here we do it's a 2 factorial by s raised to 2 plus 1, which is 3. It's a 2 by s cube. Then Laplace transform of x raised to 3 by 2. This is basically gamma of 3 by 2 plus 1, which is 5 by 2 divided by s raised to 5 by 2. So gamma of 5 by 2 is so gamma of 5 by 2 we can write as 3 by 2 times gamma of 3 by 2, which is 1 by 2 times gamma of 1 by 2, which is root pi. So which is 3 root pi by 4. So we'll use that here, which is 3 root pi over 4 1 by s raised to 5 by 2. Now from 1, if we substitute everything, we will get left side is root s times y cap of s minus y of 0 by square root of s. On the right hand side we have it's a minus y cap of s. Then for x square we will get this 2 by s cube. Then for the last time it is 8 by 3 root pi 1 divided by into 3 root pi by 4 1 by s raised to 5 by 2. Now we bring this y cap of s on this side, and we will bring this time on the right hand side. So we will rearrange everything. We will get root s plus 1 y cap of s is equal to y of 0 by root s plus 2 by s cube plus, so 3 root pi will cancel, it is 2 by s raised to 5 by 2. Now again we will rearrange everything. So y cap of s is equal to y of 0, which is a constant, divided by square root of s into square root of s plus 1 plus 2 by s cube times square root of s plus 1. again 2 by s raised to 5 by 2 square root of s plus 1. And now we need to take the inverse Laplace transform. So first of all, I think you remember the generalized expression for the Laplace inverse so we have a form like s raised to, let me write that. We have s raised to alpha, then give me a second. S minus a. So for any alpha value which is any real number, we can write this using the e integral, e of t comma alpha comma a, where which is 1 by gamma of alpha 0 to t. Okay, if the variable is x, we have to write everything in terms of x. So write like that. Xi raised to alpha minus 1, e raised to a x minus xi dz. So you may remember this expression. So let me call this expression as expression 2. So we are going to use that here. So for that we'll do some rearrangements like 1 by square root of s plus 1. We can multiply both numerator and denominator by root s minus 1. So we can write as root s minus 1 divided by s minus 1. So we have this term common in almost all the terms. So we'll then do so equation 2 we can write as by cap of s. This is before taking the inverse Laplace transform. So we are just modifying the expression. So we can write it as root s minus 1 divided by s minus 1. Then we have root s here. Then 2 by s cube root s minus 1 divided by root s s minus 1. Then 2 divided by s raised to 5 by 2 root s minus 1 divided by s minus 1. So again y of 0. So now we'll expand the terms. Like the first term will be 1 by s minus 1. The second term will be 1 by root s into s minus 1. Okay, now this one 2 into 1 by s raised to 3 minus half, which is 5 by 2. 5 by 2 s minus 1 minus 1 by s raised to 3 s minus 1. Then the last term is 2 into 1 by s 5 minus and 4 by 2, s square into s minus 1, then minus 1 by s raised to 5 by 2 s minus 1. So now you see all the expression that we need to take inverse Laplace transform can be represented using this e integral. So use b. So the e integral can be used to express all the inverse Laplace transform of all the terms here. And if you try that, the simplified version of e integral is that for certain values of e, it will reduce to the error function in its complex form, its complementary form. So for our solution, if you substitute everything, you will find y of x, which is basically Laplace inverse of y cap of s, will reduce to, let me write the solution directly so you can try this out. So you will get the solution as y of 0 times e raised to x times error function, complementary function of root x plus x square. So this is the solution. So y of 0 is basically a number that we have to give as input, then we will get the solution. So this means that this part, the first part we have here is the homogeneous solution, and this is the particular integral. So this is a solution. So you can try this, like you can substitute this solution back into this differential equation. This should be satisfied. Okay, so you can try that. Basically for x square, it's a particular solution, it's easier to check. You can take the half derivative of x square, so d raised to half of, so you are checking, so d raised to half of x square, which is from the Lacroix formula, you know, it's gamma of 1 plus 2, which is 3 by gamma of 3 minus half, which is 5 by 2, then x raised to 2 minus half, which is 3 by 2. So it's a 2 by 3 by 2 times 1 by 2 times root by x raised to 3 by 2. So it's 8 by 3 x raised to 3 by 2. Okay, root by is also there. Now you can see that on the left hand side. So LHS is basically 8 by 3 root by x raised to 3 by 2. RHS, we need to have the function minus x square y minus y, which is minus x square, then x square plus 8 by 3 root by x raised to 3 by 2. So 8 by 3 root by x raised to 3 by 2, and they match. So x square is indeed a solution, and that is a particular solution that we know. The homogeneous solution is a little complicated, e raised to x complementary error function of root x. That you can try this out using the expansion of a complementary error function, series expansion. Then you can evaluate its half derivative and then check whether the expression 1 is satisfied. Then only it is a solution, right? So so is this clear? Any question on this? So this is how we can use Laplace transform to evaluate the half derivative. Basically solve the fractional differential equations. So basically we are taking the Laplace transform of the half derivative first, but for doing that we directly cannot do that, because the exponent is integer, right? Exponent is a positive real number, not negative. So we have to split the negative part from that, like, so that we are splitting the operator d raised to half as minus half and d raised to 1. So for the minus half, or Laplace transform d raised to minus alpha of f, we can write it as s raised to minus alpha Laplace transform of f, which is not possible for alpha being positive. What I said is that basically d raised to minus alpha it is possible, but not for d raised to plus alpha, for any positive alpha. So that's why we did that here. Okay, it's not in that, it's a Laplace transform. So we split it in, then directly applying the Laplace transform of derivative of y, which is standard formula, which is s into y cap minus y of 0. Now if you simplify, you will get the root s times y cap of s minus y of 0 by root s. That's what we done. Then basically we all the other terms is a straightforward. We will take the Laplace transform directly, rearrange everything. We'll get the what we have done earlier in the Laplace transform cases, getting y cap of s, then taking the Laplace inverse. So here inverse Laplace transform, we have to use special function like E integral. Just that because the numbers we have, the E integral will reduce to mostly error function and its complementary part, and most of them will cancel, and that's why we are finally getting the solution here as x square because most of the terms cancel and the sum of the remaining terms are there still in their common integral function. So that's what we got solution. That you can try how to take the inverse and use the properties of E integral to get the solution. So I hope that is clear. So we'll move to the next question. So here it is asked to verify d raised to 1 acting on the function x with respect to x. Okay, direct with respect to x is indeed d raised to half times d raised to half of x. Basically, like 2 times you do the d raised to half and you are finally getting the same result. Just verify. I didn't specify it. I mean, you can verify this using Lagrange's formula, which is very easier to do. And the other thing that particularly what I wanted to verify here is that using the Cauchy integral formula. So not Cauchy integral formula, the Riemann-Leibniz integral formula. Okay, so for a particular a value. So first let us try the trivial one, which is using Lagrange's formula. So which is, we know d alpha of x raised to beta is just gamma of 1 plus beta divided by gamma of 1 plus beta minus alpha x raised to beta minus alpha. So that d raised to half of x. So we know this should be equal to 1, right? Because d1, the first derivative, is basically 1 for x. So d half of x is gamma of 2 divided by gamma of 3 by 2 x raised to 1 by 2, which is 1 divided by 1 by 2 times gamma of half, which is root by x. Okay, it's 2 root of x by pi. Now again d raised to half of x, which is d raised to half of 2 by root pi root x. Now the constant 2 by root pi we can take outside. Now d raised to half of x raised to half. So 2 by root pi, again using Lagrange's formula. So gamma of 3 by 2 divided by gamma of 3 by 2, so basically gamma of 1. Then x raised to 0. So which is 2 by root pi. Gamma of 3 by 2 I can write as 1 by 2 into gamma of 1 by 2, which is root pi. Gamma of 1 is 0 factor, which is just 1, and then again 1. We will see it is actually 1. So which is equal to d raised to 1 of x, which is verified. So this is using Lagrange's formula. So now it is verified. Now using Riemann-Leibniz integral equation. So we need to verify that. So first of all, d raised to half of x raised to 1. So first of all, let us write the Riemann-Leibniz integral equation. D raised to minus alpha of f of x is equal to 1 by gamma of alpha integral 0 to x minus t the whole raised to alpha minus 1 f of t dt. And this is possible for alpha's positive. So basically this is an integral expression with respect to x from a, or j alpha x from a. Now what we want here is that d raised to plus half of the function x. So which we can write as d raised to 1, d raised to minus half of the function x. So which is basically d by dx, then 1 by gamma of half using the formula, integral formula. Okay, so this is a for a general case. So a to x, then x minus t the whole raised to half minus 1. The function is t dt. So now we will take gamma of half, which is 1 by which is root pi, we will take outside. Then d by dx integral a to x t by square root of x minus t dt. Now as we have done earlier, we can rewrite this expression like 1 by root pi d by dx. So basically we need to evaluate this integral. So let me give a number. Let's say this is 1. So basically we need to evaluate t dt by x minus t integral a to x. So what we will do is you can write it t minus x plus x dt divided by x minus t a to x. So we can take the constant outside and then a to x dt by x minus t, then minus x minus t dt a to x. Like that we can split this into two integrals. So the first one is basically x minus t the whole raised to half divided by half, with the negative sign outside, minus x minus t the whole raised to 3 by 2 by 3 by 2 with the negative side commonly outside, that we already know. And now we have to apply the limit t equal to a to x, so which is minus 2, and at the limit, the upper limit, it is already vanishing, so that we can cancel with the so only the lower limit exists, so that will cancel like with the negative sign. So it's like x into x minus a the whole row minus 1 by 3 x minus a the whole raised to 3 by 2. So now we have to substitute this in 1. So from 1 we will get d raised to half of x is 1 by root pi d by dx of 2 into x root of x minus a minus 1 by 3 x minus a the whole raised to 3 by 2. So the 2 is a constant, we can take outside, 2 by root pi. Then differentiation we can apply by differentiation by parts, like first into derivative second, which is 2 root of x minus a square root of x minus a times 1 minus 1 by 3 3 by 2 x minus a the whole raised to half. 3 and 3 will cancel, so this we can simplify to 1 by root pi times x by square root of x minus a plus square root of x minus a, which again we can simplify to 2x minus a divided by root pi times root x minus a. So this is basically d raised to half of x, the first part we completed. But you can see this is actually different from what we got earlier, d raised to half of x, which is 2 root of x by pi. It's actually not that different, just that we have used a general definition of Riemann-Leibniz integral expression, which is integrated from a to x. Instead we have used the special case, like the Laplace case, where if a was 0, then d raised to half of x, you will see it is 2x minus 0 by root pi root x, which is just 2 root x by root pi. Indeed, that what we got earlier. Okay, but so that works. We already have seen that that half derivative, if you repeat again, that is going to give a panel solution. But that is not a unique way of representing the half derivative. There is another way. This, along with its definition, the Riemann-Leibniz integral definition of the half derivative, or basically a fraction derivative. Actually, fraction integral, but consistent with the derivative aspect, which is also going to give the same result. Like we are checking whether this is consistent with the fact that d raised to 1 of x is indeed 1. So it will be. So this expression is actually valid. That's what I am saying. So if we repeat again the process, we will see that. Now we are repeating this d raised to half of d raised to half of x again. So basically we are taking d raised to half of this expression, 2x minus a by root pi times root x minus a. So here also we'll take the constants outside 1 by root pi. Then we'll write it as d raised to 1, d raised to minus half. Again repeating the same process. 2x minus a by square root x minus a. So again 1 by root pi d by dx using the integral formula. So 1 by root pi integral 0 to, or not 0, a to x, x minus t the whole raised to minus half, then 2t minus a by root t minus a dt. So the 1 by root pi with 1 by root pi will become just 1 by pi, then d by dx integral a to x 2t minus a by square root of t minus a okay, I made a mistake. It's the square root of x minus a complete. Yeah. The square root of t minus a times square root of x minus t dt. Now we just need to perform the integral. So let me call this as expression, let's say 2. Okay. So the integral a to x 2t minus a by t minus a x minus t. So you can use different methods to solve this. So easier one might be you can use the contour integral to solve this, where from a to x there is a branch cut. Using the fact you can solve this integral, and there is a we can actually split into two integrals, minus a dt by t minus a x minus t from a to x, then plus 2 times t dt by t minus a x minus t from a to x. So using the fact that in the first integral infinity is also a point of singularity, which is actually a symbol pole in a sense. If you okay, not a symbol pole, but with respect to infinity you will find the residue to be exist. And here also infinity is actually a singularity with respect to which singular residue exists. So that and there is no other singularities other than a and x, which is connected by a branch cut. So the along the branch cut you will find the integral will reduce to 2 times the integral what we want, to I times, I think, and then you can evaluate them. So I will just write the expression, which is minus a times for the first integral you will find it is just pi. Second one is pi by 2 times a plus x, and you can see that this will simplify to pi a plus pi x minus pi a, which is just pi x. Okay, now you sub in okay, substitute this back in. You will see that d raised to half of x. Remember that we are doing a general definition with Riemann level integral with a, everything is included. So what we are going to get is 1 by pi d by dx pi x, which is just 1, which is indeed d raised to 1 of x. So see that even though we have generalized the aspect that there can be an a lower limit in the Riemann level integral, this doesn't matter. If you repeat twice, that everything will disappear. Will get the half derivatives will repeated twice will added up to the full derivative a1 of x, and this is true for every function f of x. You can try this out. Okay, is this clear? Any questions in this? Okay, nothing is there, so we'll stop here for today. We'll continue next week. Okay, thank you.